Hey, Bulldogs! How's it going, chemistry fans? Here for our second video, Chapter 9, talking about stoichiometry some more. We're going to get into limiting and excess reactants and what those are all about. So, let's get started. First thing to think about, here's an analogy. We've got some invitations and we have some stamps. So we're going to have a party and invite some people over. And so we got 12 invitations, but you got a book of stamps. You got 20 stamps. Well, these invitations are kind of thick, and so it takes 2 stamps to mail them. So you think, well, how many invitations can be sent out? So as we think about the combination of these two, we could think of an equation. For every 1 invitation, we need 2 stamps, so that's the I plus 2s. And then we make a set there, right? They're joined together, they're bonded, and so that's the IS2. So as we look at our ratios here, for every 1 invitation, there's 2 stamps. So as we look at our possibilities of, well, how many can we make? Well, it's not always going to work out perfect. Just like in chemistry, the amounts that we're combining for a reaction are not always going to be perfect ratios. We're going to have more of one than the other, or one of them is going to get used up first, and that's going to stop the reaction. Once we either run out of invitations or run out of stamps, we can't mail any more of those, right? So that's limiting our reaction, what we can do here. So with this one, numbers are pretty easy. If we had 12 party invitations, well, we need 2 stamps for every one of those, so we need 24 stamps. I don't have enough. I don't have 24 stamps. I only have 12. So, I only have 20, sorry. Or the other way of thinking of it is, well, I have 20 stamps, and I have half as many invitations, so I can only do 10 invitations. So when I run out of stamps, I'm going to have 2 leftover invitations, and that's going to be my excess. As we looked at the limiting in this problem is going to be the stamps. We're going to run out of stamps, and that's going to control how many invitations we can send out. So when we're doing this, and we talk about those ratios, remember, balance equation is always the number one thing we need. We need to have the molar ratios, and we get that from our balance equation. So here with our equation, and let's get a color here. We think about to balance this out, what do we need here? Well, I need to have, I've got 3 hydrogens, so I know I can't do that, so I put a 2 there. And that's going to give me 2 sodiums. I'll put a 2 there. And now I have 4 hydrogens and 2 oxygens, so I put a 2 here. And now everything's balanced out. So when we think about these ratios, what do those coefficients mean? Well, we can think about it this way. 2 atoms of sodium, 2 molecules of water. We get 2 molecules of sodium hydroxide, 1 molecule of hydrogen gas. Or the more common way to think about that is that we have 2 moles of sodium and is going to need 2 moles of water to react with it, right? Well, here's our given amounts. What if we were given 4 atoms of sodium and 2 molecules of water? Well, we see this as a 2-to-2 ratio between these reactants, which really means that it's a 1-to-1, right? For every sodium, we need water. And you can look at it either way. If I look at it starting from the sodium side, if I have 4 atoms of sodium, well, I'm going to need 4 molecules of water, and I don't have that. I only have 2. So I know that I'm going to run out of water molecules first, and that's going to make the water my limiting reactant. Well, the other way is to just flip it around and look at it from the other side. What if I look at it from the water and think, well, for every water, I'm going to need a sodium. So if I have 2 waters, I'm going to need 2 sodiums. But I was given 4 of them, so I have more than I need. So that tells me the sodium is in excess. Therefore, the water must be the limiting again. So either way you do it, you should get the same answer. More commonly, like I said, we're going to talk about moles. So if I had 10 moles of sodium and 12 moles of water, well, what am I going to run out of first? Well, I'm going to run out of sodium first this time. Again, I'm going to have extra water left over. So water is my excess. So when you think about controlling the reaction is going to stop when I run out of that 10 moles of sodium, and I will have extra water sitting there. So that's going to end the reaction. So the reason we need to figure this out is so we know how much product is going to be made. If we're trying to figure out how much hydrogen gas we can produce out of this, and it's like, oh, well, if I have 10 moles of sodium, I'm only going to use 10 moles of water. But then we think this ratio here, 2 to 2 to 1, I'm going to have half as much hydrogen. So I'm only going to make 5 moles of hydrogen gas. So we need to know which one's the limiting, because that's the one that controls the reaction. Last video, I gave you this diagram. It's a nice thing to think about. The last problem, I was just talking about moles of A to moles of B, right? Comparing one thing to the other. But most of the time, we're going to be given grams. So remember, you got to use the periodic table, get the molar mass to change from grams to moles. And then you're going to use the balance equation to go from moles of A to moles of B. And then the periodic table again to go from moles of B to grams of B. So having that paper out is helpful. So here's our example. We got some C4H10, which is butane. What kind of reaction is this? That's right. It's a combustion reaction. So with the combustion here, the first thing we need to do is balance this equation. Right away, when I look at this, I think about putting a 5 over here. That's going to give me an odd number of oxygen, so I'm going to have to double this. So I'm going to put a 2 there. That means I'll have 8 carbon. I'm going to save the oxygen till the end. I have 20 hydrogen, so I need a 10 there. So that gives me 10 oxygen from this, 16 from that. That's 26. Half of 26 is 13. So there's our balanced equation. Now, as we're setting these up, we have grams. So just like I showed you in the previous slide with our mapping, we're going to need those molar masses. So I already put those up here for us. 4 carbons and 10 hydrogens gives us a molar mass of 58.123 grams per mole for butane. And oxygen is going to be 31.998 grams per mole. So using that information now, I'm going to pick one of these. So flip a coin, whatever. It doesn't matter which one you start with. You pick one of them to compare it to the other so you can know which one is the limiting reactant and which one's the excess reactant. So I'm going to start with the 436. Get my paper out here so I can do my numbers fast. 436 grams of, here we go. 436 grams of oxygen. There we go. So first thing I got to do is get rid of that oxygen, and I know it's 31.998 grams for every 1 mole of oxygen. So next one, I'm using my molar ratios. Ooh, nice straight line there. And I want moles of O2 on the bottom to cross that one out. And I want moles of butane on top. And what's the ratio? Well, we get that from the balanced equation. It's 13 oxygen to 2 butane. A little better. So I want to get rid of moles of butane. I'm going from the periodic table, so it's always 1 mole. And then, just like I did over there, 58.123 grams of butane. Well, you crank that through on your calculator, and you should get 121.842, blah, 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 blah. We look at significant figures. We have 3 here in the beginning. We got 5 there. This is exact amounts, moles to moles. And we got 5 over here, so we need to go with the 3 of them. So that makes us round up to 122 grams of butane. This is what is needed to react all of this oxygen. Well, this is what's needed. How much were we given? We were given 275 grams. So that means I don't have enough. Or I mean, I have extra than I need, right? Sorry. I only need 122. I was given 275. So that means butane is in excess and oxygen must be my limiting. Well, what if I flipped the coin the other way and did the numbers for the oxygen? Well, you can do that, and I'll do that real quick here for you. So let's start with the oxygen this time. If I had, or start with the butane this time. 275 grams of butane. So I want to get rid of grams of butane, so my 58.123 grams for 1 mole of butane. And then I want to get rid of moles of butane, so it's 2 moles of butane. And it looks a lot like what I did up top. I'm just kind of doing it in reverse. 13 moles of oxygen. So you're going to need to do the same work anyways. You've got to figure out the molar masses. So I'm going to get rid of moles of oxygen. And that's going to be the 15.9, or sorry, 32. There we go. 32, 31 pretty much. 998 grams of O2. So you run this through the calculator and you get 984.058, which you should round to 984 grams. And this is what's needed, right? And you think, well, how much was I given? I was given this is O2 that's needed, right? I was given 436 grams. That's my given value. So I wasn't given enough, right? I'm going to run out of the oxygen. So I have excess butane. So when you think of which one you're going to run out, that's going to tell you which one is your limiting. So no matter what, the limiting is the O2. Either way you go about it. So it doesn't matter. You pick one of them and you compare it to the other reactant to figure out which one is the excess and which one is the limiting. Now, what are we going to do with that information? Well, now we think of, well, I know which one's the limiting. So from that reaction with those two amounts, I want to figure out how much CO2 is made. So I know the oxygen is the limiting, so that's the one that I'm going to use. And now, using my grams of A to grams of B, my mapping that I do, my B part is going to be the CO2 now. Now that I know which one's the limiting, that's the one I want to use. So I start with this 436 grams of O2, and I've done this, some of the numbers already, so it's not as much work as you might think at first. For 1 mole of O2. And now we look at our molar ratios. Oh, and remember, I didn't put that up there. We have 2, 13, 8, and 10. So for every 13 moles of O2, I have this ratio now. I get 8 moles of CO2. Eight moles CO2. So now I want to get rid of moles of CO2, and doing the numbers over here, 1 carbon, 2 oxygen gives me 44.009 grams. So running that through on the calculator, you get 369.0216. Again, I have 3 significant figures here. I got 4, 5 there. None here with the molar mass, and or the molar ratio, sorry. And then over here I have 5 again, so I need to round to 3. So that's 369 grams of CO2 is going to be produced. So before I know before I can figure out my product here, I had to first figure out what was the limiting reactant, because that's the one that controls how much of the reaction takes place. That's the one I need to use then when I'm trying to compare that reactant, that limiting reactant, to one of the products that I'm interested in finding out about. So we can relate any 2 things in this balanced equation using stoichiometry because we have those molar ratios. And then you just use the periodic table to figure out the moles to grams. So this process, going through systematically like we've done before, and again thinking of crossing things out, grams of oxygen, cross off moles of oxygen, moles of carbon dioxide, right? You go through this process and then you can work through it very systematically and not get confused on it. So that's the next big part, figuring out limiting and excess reactants. So go ahead and get started on that, and we'll keep working on it.